Hey. Okay, so now we're going to get to our first real video. What I'm going to do is, instead of this little infinity screen that you can probably currently see next to my big fat head right now, I'm going to pull up a PowerPoint presentation on propagation of uncertainty. Now, to me, this fills the whole screen, okay? So this is the slideshow. So I can't see what I'm doing at the time, so if I start to spaz out, just ignore it. Just ignore it. I'm doing the best I can. Unfortunately, there's no way for me to turn the video off, so you have to see my big fat head if you want to hear my relatively annoying voice, and that's just the way it is with these Panopto recordings, but better than nothing. So here we go with propagation of uncertainty. Okay, so propagation uncertainty is our topic for today. So first of all, let me talk about what we're doing here and why propagation of uncertainty is important. So often in labs, what you do is you're going to experimentally determine or measure certain values and then use those values to calculate something else. Okay, so for example, in the picture that you see down here with these poor students that are probably in something like a physics 1150 lab, what they're doing here, let's just say they're measuring the acceleration due to gravity. Okay, so they're trying to measure 9.8 meters per second squared, or little g. So what they're doing here is they're using meter sticks to measure the distances that something might fall, say off that pulley. And then what they're doing is they're then figuring out fall times, so how long it took something to fall that distance. And then from the distance and the time, they then use that to calculate the acceleration due to gravity, little g. Okay, so that's how it goes. Okay, so this is often how it goes in physics experiments. You're not necessarily directly measuring the thing that you want to calculate. You're measuring it indirectly through other variables. So what you do is you have these experimentally measured things, such as the distance, okay? And that distance will have an uncertainty associated with it, say from the precision of the meter stick. Let's say that you can only measure the distance to 1/3 of a millimeter, or whatever the precision of your device is. And then you would measure the times from a stopwatch, and you would have an associated uncertainty with that. For example, human reaction time might be a decent estimate for your uncertainty for stopwatch measurements. So using those two things, you would then calculate G. Now your uncertainty in G is going to be different from these things, and you have to propagate the uncertainty in the measurement and the time through the equation that you have for G in order to calculate what the uncertainty on G is. So that's what we have to learn how to do, and it's a skill. Okay, so what you're going to find is that when you propagate these uncertainties through equations, you're going to get an uncertainty in your final measure result that's larger, actually, than the measurements that than the uncertainties on the measurements that you've made. So the calculations, they can be kind of complicated for certain systems. If you have a really huge equation that describes what your uncertainty is, then it can be complicated to propagate that through, and so this takes practice. Okay, now remember that in the lecture that I gave, hopefully on the first day of class, we've defined absolute and fractional uncertainties. I want to caution you before I start launching into any equations that a really common mistake that students make is getting the fractional uncertainty mixed up with the absolute uncertainty. For example, some of your calculations might turn out a number of 0.35, and then students will write that down as the absolute uncertainty on their number. But that's really a fractional uncertainty, and what that means is that it's 35% of their answer. That's very different from the true value. So hopefully you'll see what I mean as we go through and keep talking about this, but just bear that in mind. What's an absolute? What's a fractional? You have to keep track of it. What we're going to assume in all the equations that I've laid out so far is that our measure values here for the purposes of these equations are going to be x, y, and z, okay? And the desired value that you have to calculate is q, okay? I'm going to make the big assumption that x, y, and z are independent of one another, and that the uncertainties associated with x, y, and z are random uncertainties. Okay? So to define those things, independent means that your uncertainty in x doesn't affect your uncertainty in y. To go back to our example that of the students in the 1150 lab measuring G. For example, the meter stick, any measurement they make with the meter stick and any uncertainty associated with that is not going to be at all affected by human reaction time on a stopwatch. So those are obviously very independent things, okay? Okay, so random now. Random means that it's not a systematic uncertainty. So remember, systematic uncertainties are things like clocks running slow, meter sticks where the divisions aren't correctly laid out, things like that. Consistently, in other words, under or above the true measurement, one or the other, under or above. Okay, so let's launch into the formulas for the calculations. I want to first say that in Chapter 2, your book lays out all kinds of provisional rules. Now, I'm not going to go over the provisional rules, and I don't want you to use them in any of your calculations. We're going to use the hardcore stuff, okay? We're not going to go provisional. So these are the real, tried and true values for propagating the uncertainties through the equations. Let's use those. So for addition and subtraction, let's say that you're calculating some value q and you have to add or subtract x, y, and z to get that q. What you do to find the uncertainty in q, delta q, is the square root of the sum of the squares of the uncertainties in x, y, and z. So here I'm using the notation that that lowercase delta value is the uncertainty, indicates the uncertainty. Okay, now if you're multiplying an experimentally measured value by a known constant with no uncertainty, for example, 1/2 gt squared is equal to the distance fall, right? So you know 1/2 precisely. Okay, so in that case, let's say that you have a formula q is equal to bx, where b is your precise constant. In that case, what happens is the fractional uncertainty is preserved. So if you have, for example, a 5% uncertainty in x, then you're going to have a 5% uncertainty in q. If you don't want to calculate fractional uncertainties, then the way to find your uncertainty in q delta q would be to multiply your constant b times your uncertainty in delta x. So delta q is b delta x. Let's do an example using these two ideas. So this is a problem that I think I took from your text. Given the following measured values, find the average and its experimental uncertainty. So our values are 11.3, 12.1, and 13.6, and they all have an uncertainty of plus or minus 0.5. Well, we know how to take an average. That's pretty straight up. Hopefully you've got that one memorized by now. So the way to take an average is you sum up your values and then you divide by the number of values that you have. So in this case, you're summing 11.3, 12.1, and 13.6, and that sum gives you 37. And then you have three values. So 37 over 3 gives you 12.33. So that's your average. Now, remember what we said about how to propagate uncertainties. So the first thing that you're going to do is propagate the uncertainty through that addition of the values 11.3, 12.1, and 13.6. So our rule for propagating uncertainties in a sum or a difference is the square root of the sum of the squares of the absolute uncertainties. The absolute uncertainties here are 0.5 on each of those numbers, so to find the uncertainty in the addition part of it, it's the square root of 0.5 squared plus 0.5 squared plus 0.5 squared. Wow, I'm losing papers. Sorry. That gives you 0.866. Okay, and then to find the uncertainty in Q, you're going to be dividing, multiplying by a known constant. That known constant would be 1/3, so you're multiplying by 1/3. So what you do is you take 0.866, your uncertainty, and you divide it by 3, and you get delta Q is 0.289. But now that's not what you report. Remember, our rule is for uncertainties that you keep at most 2 and preferably 1 significant figure in your uncertainties. So what we would do is we would round up, 0.289, round that up to 0.3, then we would match the precision of our uncertainty to the precision of our value. So what we would have is 12.3 plus or minus 0.3. So there you go. All right. Now notice that I did a couple of things, and I'm going to go over these. If there's more than one step, what you're going to do is you're going to round at the end when you report your final value. If you remember from the previous slide, I kept digits. I said 12.33 and 0.289, and I didn't round until the very end when I reported my final value. That's what I want you to do. Otherwise, you're going to get rounding error. Next, if there's multiple steps, make sure that you follow order of operations in the main calculation of the value and when you're propagating the uncertainty. So there's an understood bracket around that addition of the values, of the 3 values in the previous problem. You have to add them first and then divide by 3, your known constant. Okay, so that was the order of operations for that one. In general, what you do in order of operations is first you do any brackets, then you do exponents and any roots, then you do multiplication to division, and then addition and subtraction comes last. Okay, if you need some kind of review on order of operations, I've given a wiki website here at the bottom where you can review it. But make sure that you follow order of operations if there's multiple steps in the problem. Okay, so moving on, multiplication, division, raising to a power. Here we have q is equal to x times y over z, so you're multiplying and dividing. Well, if you're multiplying and dividing, what you're going to do is work with fractional uncertainties. Before, in addition and subtraction, we were working with absolutes. Now we're going to be working with fractionals. So here's how to find the fractional uncertainty in q. Delta q over q is the square root of the sum of the squares of the fractional uncertainties. Okay? All right, if you're raising a measured value to a power that's known exactly, so for example, the formula here is q is equal to x to the n, where n is some number that we know exactly. Yet again, to fall back on the simple kinematics example, if d is equal to 1/2 gt squared, then the squared is known precisely. There's no uncertainty on that too. Okay, so in that case, then you have the fractional uncertainty in q is going to be the power times the fractional uncertainty in x, okay? Absolute value. All right, so another example, this is problem 23 in chapter 3 of your book. In an experiment on the conservation of angular momentum, a student needs to find the angular momentum of a uniform disk of mass 1.1 plus or minus 0.01 kilograms and radius 0.25 plus or minus 0.005 meters as it rotates with an angular velocity of 21.5 plus or minus 0.4 radians per second. What's the answer for the angular momentum and the associated uncertainty, remembering from physics 1150 that your angular momentum of a disk is going to be 1/2 mr squared times omega. All right, so let's work this problem. So first of all, it's easy to calculate your angular momentum. You just plug and chug into the formula that you're given. So you get 1/2 times 1.1 times 0.25 squared times 21.5. And if you do all that, you get an angular momentum of 0.739. Okay? Okay, now what we have to do is we have to propagate the uncertainty through that equation. So first, following order of operations, we've got the r squared. Remember, powers and exponents come before multiplication. So we're going to propagate the uncertainty there first. So our fractional uncertainty in the r squared value is going to be the power times the fractional uncertainty in r. Okay? So that's, the power is 2 because it's squared, and then the fractional uncertainty in r is 0.005 over 0.25, and that gives you 0.04. Now remember, this is a fractional uncertainty. It's tempting to write that out as an absolute, but what this 0.04 means is that there's a 4% uncertainty in the value of r squared. Okay, next we're going to multiply. So we have to multiply m times r squared times omega. All of these are experimentally measured values. They all have uncertainties associated with them. We're going to follow the rules for multiplying and dividing. So here, it's going to be the square root of the sum of the squares of the fractional uncertainties. We've already calculated the fractional uncertainty in r squared. That's 0.04. So I just go ahead and stick that in the equation and square it. And then I add in the uncertainties in m, which is 0.01 over 1.1. Square that. And your value for omega, 0.4 over 21.5. So we do all that in. If you do this, then you get 0.045. Yet again, this is a fractional uncertainty. So that means that when you multiply m times r squared times omega, you have a 4.5% uncertainty in that. Now, we then multiply times the known constant of 1/2. There's no uncertainty in that number. That means that the fractional uncertainty of 4.5%, that's preserved because you're multiplying times a known constant. So we can use this 0.045 and our value of L, which you've already calculated, to find the uncertainty in L. We just multiply 0.045 times 0.739. We get 0.033, and that's our uncertainty in L. Now, I don't want to report it like that. I guess I could, because I said 2 or less, and 0.033 is 2 sig figs. But I'd rather just keep 1. So the final value that I'm going to report for my angular momentum is 0.74 plus or minus 0.04 kilograms meters squared per second. Remember, if that went too fast for you, you can always pause it, rewind it, whatever you need to do. And the slides are posted online. Okay, finally, the last bits and the most difficult bits are the general formulae for one and multivariable equations. So let's do the one variable general functions. Okay, so if you have q is just some function of x, okay, then the way to calculate the uncertainty in q is to take the derivative of q with respect to x and evaluate that, the absolute value of that, and then multiply it times the uncertainty in x. Okay, the example that I'm going to do is about the trig functions. Okay, I'm going to specifically cover sine and tangent. So, for example, let's say that you've measured theta, you've measured some angle theta, and you want to find the uncertainty in the function sine of theta. So, the way to do that, delta sine of theta is going to be the derivative of sine of theta with respect to theta times the uncertainty in theta that you measured. Well, the derivative of sine theta absolute value is going to be cosine of theta, so it's cosine of theta times the uncertainty in theta. Now, if you want to find the uncertainty in tangent theta, it's the same basic steps. You're going to take the derivative of the tangent at theta with respect to theta. That gives you secant squared of theta. And then you multiply that times your uncertainty in theta. Okay, one thing that I want to emphasize with trig functions or anything involving an angle is if you have to go through an uncertainty calculation through that, you have to put your angle in the SI unit for angle, which is radians. Okay, so make sure that you convert your units from degrees to radians if degrees are given. Okay, so I want to use this idea now in an example problem where we're thinking about the small angle approximation. So you might have heard of the small angle approximation already. If not, here it is. The small angle approximation says that for small angles, the value of sine of theta is approximately equal to theta. And sometimes they also say that the value of tangent of theta is approximately equal to theta as long as theta is in radians. Okay, so let's evaluate what the experimental uncertainty here is and calculate that and figure it out. Okay, so we already found this on the previous slide, that the delta sine of theta was going to be cosine of theta times delta theta. That's our uncertainty in the function sine of theta. Well, for small angles, theta is really close to 0. So that means that cosine of theta is going to be really close to 1. So what that means is that your uncertainty in the function sine of theta is going to be roughly the same as your uncertainty in theta. And this is kind of where this idea comes from of the small angle approximation. Okay, let's talk about tangent of theta. The uncertainty in tangent of theta is going to be secant squared of theta delta theta. Okay, so that's secant, in case you've forgotten, is 1 over the cosine. So that's 1 over cosine squared of theta times delta theta. Now, since the cosine function here is squared, all right, deviations from 1 are going to show up a little bit more quickly. So it's still a cosine, and 1 over the cosine squared of 0 is still 1, all right? So that still gives theta, the uncertainty in theta, as our uncertainty. Pretty close. But since the cosine's squared, the further and further you get away from theta close to 0, the bigger the discrepancy is going to be, okay, from that value. So what we can say is, well, gee whiz, the small angle approximation should hold for longer for a sine function than it should for a tangent function. So let's see if that's true. Now, here's where you're probably going to need those slides that are posted online. This type might be a little small to see in the Panotto video. Go ahead and pause me if you need to. Please do. Actually, I want you to really study this and take some time to look at it. But let's discuss it like you can actually see it, and then you can pull it up later. So first of all, this is an Excel file that I made just to quickly demonstrate this idea. So the first column is theta in degrees, and then in the second column I've calculated theta in radians. I've done that conversion, which is, of course, 180 degrees is equal to pi radians. Okay, next I've calculated the sine of the angle theta. Okay, so that's done in column 3. And then what I've done is to calculate a percent error of that value. So I compared theta to sine of theta. Remember, the formula for percent error is the value minus the true value, those two things, and then divided by the true value times 100%. So that's what I've got there for percent error. And you can see that this is actually under a 1% error all the way up to 10 degrees. So it's a very good approximation for angles less than 10 degrees. It's less than a 5% error all the way up to 30 degrees. So that's really pretty good. Only after 30 degrees does it start to get bigger and bigger. Okay, so now let's look at tangent of theta. Okay, so if you calculate tangent of theta, that's in the next column. What is that? 1, 2, 3, 4, column 5. And then the percent error comparing tangent of theta to theta in radians is in column 6. So you can see if you look at it that it's still 1% error or less up to 10 degrees, but then after that you can see that tangent of theta, the percent error, is much larger than it is for the sine of theta approximation. In fact, at 50 degrees, which is the very bottom, you've got a 36% error for tangent of theta. It's approximately equal to theta, as compared to a 13% error for sine of theta is approximately equal to theta. So it does blow up a little bit faster, which agrees with what we've been arguing here in our previous bits. Okay, so now let's make a nice assumption in what our uncertainty for an angle would be in, say, an experiment. So a 5% experimental uncertainty is completely normal and not unheard of. So then after the break in the columns, that's my 5% of theta. So that would say be our uncertainty in our angle. And then I calculated our uncertainty in sine of theta and our uncertainty in tangent of theta in the last two columns there, given a 5% uncertainty in our angle. So if you look at that, then you can see that the uncertainty for tangent of theta is larger than the uncertainty for sine of theta, all down the column as we predicted and as we expect. So do spend some time kind of studying that and giving that some thought, because this is a more complex example. You'll probably have to pause it or at least go back and look at the PowerPoint later. Okay, last big idea, multivariable general function for error propagation. This is if Q is a function of x, y, and z, or however many variables you've got. Okay, so in general, what we can say is that the uncertainty in Q is then going to be the square root of the sum of the squares of the partial derivatives of Q with respect to each of our variables times the uncertainty in that variable squared, as it's laid out here. Okay, so let's first of all remember what a partial derivative is. Remember that, for example, partial of Q with respect to Z is the partial derivative of Q with respect to Z. To take a partial derivative, what you're going to do is you're going to take everything in the function for Q except explicit functions of Z, and you're going to hold those as constants. So the simple example that I've put up here is if Q is equal to x squared times y squared times z squared, then x squared and y squared would be the constants here. We treat those as constants. And then taking the derivative of z squared, we get 2z, okay? And so we have 2z times our constants, x squared and y squared. Okay, if you need a little refresher on partial derivatives, or you've never seen them before and you want a little bit more information, then you can go to the Wikipedia link that I've laid out here. Okay, so let's do an example problem with this multivariable error propagation. So let's just say Q is equal to x e to the minus y. And x is a measured quantity, 20 plus or minus 2, and y is also a measured quantity, 1 plus or minus 0.1. So we're going to find Q and its associated uncertainty. So first we have to evaluate these partial derivatives of Q with respect to x and with respect to y. So the partial derivative of Q with respect to x, we would hold e to the minus y as a constant. So the derivative of x is 1. So here, partial of Q with respect to x is e to the minus y, and then we need to evaluate that at the measured values. So e to the minus 1 is about 0.3679. See here, I'm keeping lots of digits. I'm not going to round till the end. Next, partial of Q with respect to y, we hold x as the constant, and we just take the derivative of e to the minus y, which is minus 1 e to the minus y. So here for partial Q with respect to y, minus x e to the minus y. And then plugging in the values for x and y, we get minus 20 times e to the minus 1, which is minus 0.73576. Now, we want to plug those partial derivatives that we found into our formula for our uncertainty in Q. So that gives us the values that you see here. Plugging in the numbers for that, we get, of course, the partial of Q with respect to x was 0.3679, and then times the uncertainty, delta x, which is 2. So 0.3679 times 2, and then you square that. And then plus minus 7.3576 times 0.1, quantity squared. And then when you evaluate that square root, you get 1.041. So that's your uncertainty delta Q. Now Q, if you plug in values of x and y that we have, is 7.3576. So what we would report, keeping 2 sig figs, I kept 2 this time, was 7.4 plus or minus 1.1 for Q. So that's how to handle those multivariable functions. All right, now I have to say that this error propagation is something that we cover in the very beginning of the semester, and it's a skill that you're going to use throughout the semester, and it's also a skill that you're going to have to continue to use when you take Physics 4210, Methods of Experimental Physics. So make sure that you keep up with this and don't de-emphasize its importance, and I'll see you in class.